Hello everyone. Please confirm can you hear me? And do you see the entire slide that I'm showing here? Because I have certain issues on my side. So please confirm on chat, can you hear me and do you see everything? Because my streaming software says, okay. Okay, thank you Mr. Rolla, we can then start. Okay, so we'll talk about likelihoods and data modeling, which you see I have a bit not updated slides, but that will be fixed at some later date. I forgot to update the slide. So to sum up what we have already did before, we have covered the idea of data generating process. So the full description of how data is being related from actual phenomena occurring through effects that we can actually observe and the observation process that results in some kind of data. We did a few examples like sampling of the surface of the earth, or we did an example of how to show the of how to measure the temperature of coffee in a cup in a situation where the coffee is we only have a possibility to measure using our own hands. By the way, I have messages from YouTube that there are low quality of stream. If something like that happens, please let me know. Then perhaps we'll reschedule our lecture for this evening and I will just do the stream on more efficient connection, because I'm at the moment at AGH and as you can see it's less than optimal. Either way, so we discussed data generating process. The data generating process is something that we strive to create a model of, because if we know how the data is being generated through the phenomena we are interested in, we can construct reasonable inferences regarding the data from the we can infer how the data was created, so how the phenomena operates, how the thing we want happens. And this can have multiple situations, like for example we want to check if something is faulty but we have a noisy data and the fault is in a place that we cannot measure directly. So we need to infer, does the fault actually occurred, or is it an effect of noises, or is this just a normal but volatile operation? We discussed two tools that we'll be using more during our course, which are prior and posterior predictive distribution, with the second one being also called in literature retrodictive distribution. In general, the idea of those distributions is that because Bayesian models are generative in their own nature, we can use our prior knowledge or posterior distribution to sample parameters of the phenomena we are interested in, and using our model of data generating process, so the actual likelihood, we can sample possible outputs of the process, possible measurements that can happen. So we can simulate what kind of measurements we can expect from our prior knowledge, and we can also sample what kind of outputs our model expects, provided the data and the structure we have used. This is a useful diagnostic tool allowing us to select the prior parameters of the models, to check our assumptions if they are reasonable. Because, for example, we can confront our expectations about the outputs with real outputs and see, oh, this, what we actually observed, is not possible for our model to obtain, so our model needs to change. Or in case of posterior predictive distribution, our posterior model expects outputs to be here, and if they are not here, well, there's some kind of inconsistency between the data and how we understand how the data are being constructed, and this is verifiable through such simulation. And we did some analysis of binomial data, especially binary data, so something that is yes, no, it happened or it didn't happen. Such things are solutions for options in our process. So we've considered coin flips, we considered BIF with certain defects, we considered looking for water on a surface. All those ideas show that there something is or is not happening. And of course, natural binary variable is, of course, classification. Something is faulty or something is healthy, something belongs to a certain category or does not. So, those were the tools that we've covered before. But we can encounter multiple kinds of data. We can observe limited trials consisting of fixed number of events that can happen. For example, we have 10 patients and only 5 of them had responded positively to a treatment. Or we did 10 experiments and only 3 of them provided results. And we did those batches of 10 experiments in multiple cases. We have situations that certain events can happen. Those events can happen between one and those events can happen in situations that, for example, the number of accidents that are happening in each city, number of arrests, numbers of resets of an IoT device, etc. We can observe waiting times, so situations that what time passes between two events, or what is the remaining useful life of a device when it will fail. So, or we can have real numbers, so numbers that can take any kind of value, potentially from plus to minus infinity. So having large numbers allows us to create a solution that is the model of the phenomena that is important. So it can be money, it can be numerical gain of something, multiple numbers are possible, but sometimes those numbers are constrained, probabilities are constrained. So determining the probability of is something belonging to one class or another is a constrained number. Or we can have just constrained number because the physics of the process allows us only constrained number because it's either positive or less than 5, let's say, and only those constrained numbers are possible. So those are typical data that can happen, or percentages, or something like those data can happen. We can encounter those data, and we need to be able to create our model that handles this type of data. Because we cannot use a model that works in integer to handle real numbers, and the opposite is the same. If our results is binary, we cannot expect that we will just be using our model will be returning numbers between minus and plus infinity. Binomial distribution, which we focused before mostly on the special case of Bernoulli distribution, that is a binary situation. But binomial distribution is a distribution when we have n trials, and each of those trials has binary result. This is a very important aspect because it can represent many important cases. For example, when we consider race drivers in Formula One, we have 20 drivers on a field. So to determine the positioning of the driver, we can use a binomial distribution because our driver has passed 20 of a certain number of the other drivers, so had success against certain drivers. So our result will be a number between 0 and 20, or more practically 0 and 19, for each of the drivers. So modeling this driver's behavior will be useful to do a binomial distribution. Binomial distribution can correspond to percentages. So if our result is a percentage between 0 and 100, and we have percentages given as an integer percentages, we can then consider the binomial distribution that will represent the number between 0 and 100, so the number of successes in 100 trials. Again, if there are some issues with string quality, please let me know what is going on. Okay, so as I mentioned, special case is Bernoulli distribution, which is very simple because it has only one trial, so much easier number to compute. The distribution has the form as given in the slide. However, what happens if there are more possible results than 2? What's happening then? Then we have k possible outcomes of which we observe xi number of successes or events certain trials. So this is a simple case of classification of multiple results. So we have there are multiple possible options, and we are interested in assigning the appropriate probability, so constructing a likelihood of our proper assignment. So one of the easy examples of multinomial distribution are the election surveys, where we have multiple candidates and only one spot to happen. So people will vote for one of the 3 options. And in case of we are discussing is an American election from 1988, where George Bush Sr. was running against Michael Dukakis, the Democratic candidate, and CBS News has created a survey of 1,447 adults, out of which 727 supported George Bush Sr., 583 supported Michael Dukakis, and 137 said that they will vote for an independent candidate. So there are certain issues of modeling the probability in the multinomial distribution. First of all, we instead of probability of an event, what we had in binomial or Bernoulli distribution, is now a vector of possible probabilities of given of certain candidate winning. And this vector is not a simple vector, but is a so-called simple vector and a normal vector, or in other words, like typical vector where we can assign any number to. No, this vector is a simplex. Simplex, that is a vector that consists of values, of positive values, which sum up to a 1. And we need to include in our modeling language, in our modeling procedures, to include such construction, which is a simplex, and model it properly. We need to assign some kind of, as always, we need to assign some kind of prior distribution of P. And actually, providing an appropriate prior for P is not that obvious, because we need to assume equal probability of each event happening, and setting uniform probabilities of each of those individual probabilities will not result us with a simplex. What we see here is a so-called trinary plot. This is a good plot for showing interactions of simplexes, so three variables that one of those variables is uniquely determined by other two, because in this case P3 is equal to P1 plus 1 minus P1 minus P2. So what we would really like to have, considering the uniform prior on P, is to have this triangle of interacting three variables summing up to 1 to be equally, each point to be equally probable. Because when we create such a vector, then we have such prior. This prior does not look uniform in marginal distributions. What I mean is that our prior that is uniform over the space of all possible, all these three element simplexes, when you look on each individual probability, those probabilities will not be uniform. Those marginal distributions of individual parameters will not be uniform. They will be some kind of like this, which is in a certain way logical, because when one of those parameters is equal to 0, close to 0, we have a lot of flexibility with other parameters. However, if one of them is equal to 1, our flexibility to other parameters drops to 0, because they have to be equal to 0, so it's all something. If we use our uniform prior to sample possible results for each of those candidates, we will of course get similar situations, similar number of votes. As you can see here, we have the uniform probability distribution between all three candidates. Here we have the sampled values, generated values using prior predictive distribution, the appropriate values of number of votes for each of those candidates. If, however, we introduce data, then it becomes much more clear, because our uniform prior, when confronted with the data, constricts itself, concentrates around values, certain values of parameters. And as we can see here, we can see that posterior predictive distribution shows that in this case, the simulated number of votes for each of those candidates centers around the true value from the data, and the parameter values are also estimated in nice concentrated way, which we can see here. So the values of parameters for each of those candidates is located as we see here. Excuse me. And this is a very simple case, again, of sampling from a multinomial distribution. Integer valued samples are not limited to that case. Our most typical situation is how many events can happen in certain period. And those events are, of course, can be any kind of discrete events, independent more or less of each other. For example, police stops of drivers, devices breaking, numbers of resets of certain device per day, and other. Poisson distribution is one of the distributions that handles such integer kind of events. Its relatively simple form can be obtained by taking an appropriate limit transformations of values from the binomial distribution. And in such case, we have a so-called intensity parameter, the parameter of an always positive parameter that allows us, that represents how certain event is likely to happen in a given period, or how many events are on average probable to happen. What is important in case of Poisson distribution, besides its possibility to generate numbers of events occurring, is the fact that the mean and variance are equal in this distribution, and that means that the higher the possible, the expected value of events, the higher the variance of it. So how much distributed it can be from that value. Let's take an example of Poisson distribution, which is the number of airline accidents in a decade from 1976 to 1985. The later number of flights were such voluminous that those data would be harder to analyze, and this dataset is really clearly available for the possibility. We have a data set that includes number of accidents and number of passenger deaths in a given year. We can obtain also the death rate and the number of miles that were flown during the entire year. As you can see, during the decade, the numbers of miles flown over a plane, and each of those is multiplied by 100 million miles, it practically doubled during that period. And we will not be discussing the prior predictive check, prior selection that much, because we will cover later, but we can use prior predictive checks to generate, to verify if our prior is consistent with observed data. And we can use certain probability distribution, in this case half normal distribution, to assign the lambda value in such way that will be consistent with our data. And we can see here are the observed samples, and this is the prior distribution for this is the prior distribution lambda, and these are the simulated amount of accidents if samples were taken from the prior distribution. If we, however, introduce the data to the model, we can see a significant concentration of samples. Because as we can see, we can get rather good representation of lambda that is happening here. And because our prior from the very wide one here constricts itself to this interval of approximately from 22 to approximately 26.5. And while actual data are not contradicting these results, this is not necessarily a good representation of reality, especially that every year we change the number of flights. And that happens because we have not used the available information. There was an information about how many miles were flown, and we can incorporate it to our model, formulating a parameter as a functional relationship. So instead of our intensity lambda, we will have a new parameter that is dependent on the number of miles flown each year. And we formulate it as lambda equals to theta n, and it puts each of the data points in certain context. However, this requires for us to consider constraints and appropriate prior selection. So we need to simulate again those values to improve our results. And of course, changing the priors, we don't have a problem with number of accidents because it's still consistent with our prior. This prior was selected in a very basic way, just showing how many accidents are possible to happen every year. If we move to our model, we see that there is some kind of change in each of the year. We can see that posterior, of course, concentrates, however, this time on different scale. The parameter is not as easily representable. And we see that while there is certain improvement, still there is an issue that there is a systematic difference between number of accidents that our model predicts and the actual number of accidents. And we can see that in the earlier years it underestimates that number, and in later years it overestimates that number. And what can be cause of this? Well, perhaps the fact that we assume that despite the time passing, there are no changes in the risk of the accident happening. And of course, safety procedures are being introduced. There are some kind of technological advances that change that risk each of the years, but our model does not include it. However, you can, for example, introduce such model and see that certain safety procedures, perhaps introduced in certain years, allowed to reduce the number of accidents that can happen. And of course, we can use our Bayesian model to create predictions using the same way as posterior predictive checks. So we can use new data in this example, for example, miles flown in 1996, so the after the time we've computed, and we can then sample the probability of accident happening per each of miles, so corresponding to a theta, and we do this, of course, through sampling. So we sample a cloud of points from our posterior predictive distribution, so our posterior distribution, that we will get each values of theta for each sampling. Usually, because we are using Hamilton in Monte Carlo and Stan, we will get 4,000 values of theta. Using that new provide information about number of miles flown, we can then use theta to each of those theta to create a new prediction of how many accidents will happen, and this is analogous to posterior predictive checks. In posterior predictive checks, we just use old data, and here we introduce new data with samples of parameters. And analyzing distribution of predictions, we can make some kind of decisions or evaluate our model. In this case, our predictions are much higher than actual number of accidents, which we, as we discussed before, can be attributed to changes in safety protocols and generally improvements of safety technology in flights. What we should also note here, I wanted to add a slide, but during the restart of computer I mentioned on the chat before, there are also other distributions that can be used for modeling such events as discretely occurring events. And those tools are, for example, inverse binomial distribution, which is a distribution that is very similar to Poisson, but it introduces additional parameter, either dispersion or other, that allows you to vary the mean and the variance of distribution. If you remember from a few slides ago, Poisson distribution had the mean and variance equal to the parameter intensity parameter lambda, or in case of more advanced models, the computed intensity from parameters and predictors. If we, however, expect either bigger variance or smaller variance, we can change that, and that's what the negative binomial distribution is for, which introduces either concentration or dispersion parameters, because there are different parameterizations that allow you to differ those two parameters one from another. So in case of discrete data, Poisson is not only option, the inverse, the negative binomial distribution certainly is an option, and moreover, negative binomial distribution is a limiting case of the Poisson distribution is a limiting case of the negative binomial. So changing the dispersion, we can to appropriate value, we can obtain the Poisson distribution directly. But those are integers. However, certain data, we can ignore most of data occurs in as real numbers, and those real numbers behave in different ways. We'll focus today briefly on just natural numbers, which especially come from sums. Sums of events, because if we have a lot of data that each number is represented as a sum of events, that is generally a good idea to use a normal distribution. Because Gaussian distribution arises from addition. This happens because of the so-called central limit theorem. The result that you probably heard about it but not necessarily understand. And central limit theorem is a theorem that says that a sum of independently distributed random variables is a normally distributed one. It doesn't mean that not exactly is a normal distributed value, but is as n approaches to infinity, it tends to a normal distribution. Normal or in other ways Gaussian distribution. And this is important because people often think that central limit theorem says that if we only have enough data, then that will be a normal distribution. But that is not necessarily true. We need to have that data to represent something that is an addition. For example, growth of a person, their height, is a result of a sum of growth spurts. People do not grow as an incrementation of their own height. Because of that, it is natural to use normal distribution to modeling height of the person. But we'll do a simpler example that arises on a football field. Let us consider that we stand on the middle of a football field and we flip a coin. If we get heads, we make one step to the left. If it flips heads, we move one step to the right. So we randomly move a step from one to another. So let's focus on where we will be when we will make our steps in the same way multiple times. So let's take like 1,000 of people, we put one of those people on the middle, make them flip a coin and move right or left depending on the result by the distance they prefer. And perform this activity a number of times, let's say 16 times. Because of that, and after that we will register the position along the line of the football field. So, in this case, we will get a number somewhere between 0 and 16, because we are making 16 steps, and we have a number that corresponds for that person to their position, which is a sum of their steps into multiple places. So we have repeatable events independently distributed, because flip of each coin is independent on the previous one, and we just move around. And as you can see, after 4 steps, the histogram of that behavior becomes kind of bell-shaped. After 8 steps, it becomes even more bell-shaped, and at 16 steps, it is indistinguishable from the normal distribution, which fits perfectly. So normal distributions are, in a way, very useful tools to work with the data that arises from additions. So, but not only addition, but generally multiplication. Generally, all kinds of increments are normally distributed as long as we focus on reasonability of those increments. But that's not only those. If we multiply numbers by one another, especially by numbers close to 1, so having a small percentage changes, adding a 1% to something does not make a problem. It still can be considered an normal distribution of increments. However, in case of large multiplication, so multiplying by large numbers, then so our final value is a result of multiplication of larger numbers, not close to 1, but generally large numbers one another, then of course this is not normally distributed, because normal distribution only works for increments, and multiplication by large numbers are not increments. However, if we take a logarithm of that multiplication of large elements, we will receive a sum of logarithms of all those elements. And after summing, and in that case, our new distribution of sum will behave as a normal distribution on a logarithmic scale. Or, in other words, can be distributed by a log normal distribution, which is exactly that distribution that behaves normally on a logarithmic scale. And using normal distribution is a very natural way to describe the plausibility of given observation in a considered model. So we can explain how our data point fits our preconceptions about both model and uncertainty at the same time. Because in normal distribution, we expect that certain number has a that numbers have a mean and have a standard deviation. And probability of y given mean and standard deviation is given by this formula. But also it can of course be used as a likelihood. So we can consider that mi and theta are values of parameters that come from probability distributions, and we can compare them with our output. So the square of the difference between value observed and the mean of normal distribution is generally our contribution to the error. However, it's what is important. It is of course divided by the standard deviation. So if standard deviation is high, then of course what is the numerator is much less important. The biggest benefit of normal distribution is that when we have multiple observations and we create likelihood for each of those parameters, we can multiply them, each of those for every one. Moreover, by the normal distribution properties, they can concatenate to one distribution governed by the average of the measurements. One example of using the normal distribution is determining the speed of light. This is a so-called a Newcomb experiment of that data is publicly available of how to estimate the speed of light. This is not estimated, of course, on the scale of kilometers per second. It's analyzed as a difference from the measurement value and certain preconceived value. And such speed measurements we've obtained two very small measurements, and most of them are focused around here. This is very well described in the Gelman's book, Bayesian Data Analysis, 3rd edition. Book is free, available, you can download it online. We can use normal distribution to create certain model explaining like what the mean would be a speed of light and in this scale, and sigma would be uncertainty about it. And we can use, in this case, kernel density estimators to analyze how the posterior predictive results will look like. And we can see that the mean of posterior predictive distribution is like this. They are concentrated here. What is perhaps important is the fact that what is happening here is not, so the observed data is not being included in that model. So if we estimate the actual speed of light using this model, we will have some problem that we will fail because there are outliers happening, and our Gaussian model is sensitive to outliers. That's why Gaussians were often the first choice, are not necessarily the only choice. Setting up the probability distribution using the normal distribution gives you the sensitivity to outliers, which might be an issue or might not. Normal distributions are easier to compute, so we usually start with normals. However, when we estimate the speed of light using normal distribution in this data set, we will have an error which is a systematic move from the actual speed of light and is being caused by those outliers. And fact that we like normal distribution doesn't mean that we can only use normal distribution, and there are different distributions. One of the popular distributions on real numbers that can be used to handle such effects of outliers is the student T distribution. Student T distribution is a distribution that arises in certain analytical computation regarding normal distributions, but generally has the same property as a normal, that it's a kind of a bell curve that is concentrated in the middle. What differs is that normal distribution assumes that values that are far away from the mean are very not probable. It generally happens that moving away 3 standard deviations away from the mean will reduce the probability of even happening to less than 1%. So it causes that the probability density function is very, very close to 0 for values greater than 3 sigma. In case of student T distribution, this not necessarily happens. Student T distribution is governed by the parameter eta here, which is called the number of degrees of freedom. This is called a number of degrees of freedom. However, it does not need to be an integer. It can be a positive real number. Just the interpretation as with degrees of freedom is not that obvious. The student distribution is, as you can see, a bit complicated, including all those 3 parameters in the construction. Moreover, when parameter eta takes values of 1 or below 2, it becomes more problematic distribution, because generally student distribution, because this value becomes very small, this value becomes very small for distance, or becomes small for the distance, large distance between y and me hat, depending on the number of degrees of freedom, it will still have some probability in the student T distribution. This is so-called heavy tail distribution. That is, unlikely events are also probable. Not highly probable, but certainly possible. And depending on the eta parameter, the degrees of freedom parameter, we can get two kinds of the spectra. One, if eta is coming up to infinity, then data then it becomes a normal distribution. So our distribution becomes normal. So when we automatically select those parameters using, for example, Monte Carlo sampling, we will get the values. If values are going very, very high, there's probability that it's just normally distributed data and we shouldn't play with students. However, if it gets smaller, the tails are becoming heavier and heavier. So we are getting some situation that certain unlikely events can happen. And this is the cornerstone of robust modeling, of how to set up the distribution that won't be as sensitive to outliers. So the unlikely event can happen, okay, but most of the events still will happen somewhere. And if we replace the standard, the normal distribution with the student distribution, we can improve our estimated speed of light by moving from the mean of the Gaussian model more towards the actual speed of light. And it can handle outliers, but of course it won't handle the simplicity of the original experiment. That was still a bit flawed. Gaussian distributions are generally based off so-called linear models. The same calculations can be done with also non-Gaussian distributions. However, Gaussian distributions has a very large advantage of that, because it's if we have multiple data points, it becomes a product of exponents. All those exponents can be grouped together and done something with them. In case of student distributions, we don't have that comfort, so student distribution results are being computed mostly numerically. Gaussian distribution can be computed analytically or using the analytics computations as an introduction. We can handle we can improve our numerical computation. Linear models allow us to handle relationships between measurements and predictors in the likelihood by appropriate relationships of linear relationship between the model parameters for which we assign appropriate priors. And linear models are something that we learn very early, that come from so-called linear regression, which we won't be trying to use that formation, and we will be saying about linear models. But when we discuss linear models, we generally mean linear regression. But regression word is very loaded, so we will focus on just linear model. And linear models come from the Taylor expansion, because every nonlinear relationship, as long as it's not completely flat, can be well approximated locally by Taylor expansion, and practically, for our purposes, a linear expansion. This can be so only the first term of Taylor expansion. Of course, this has its risks, but often can be very well used. So, using Taylor expansion, we can create a linear model which will become actually a linear regression to our model. And an example of Bayesian linear model is creating a relationship in the model, saying that, okay, our mean is not actually a fixed mean of normal distribution, but for each of measurements, the mean value of actual phenomena of interest that is related to the measurement is related to the predictor in a linear fashion. So, for example, it has an intercept, so a constant term, and predictor value is multiplied by beta. And alpha and beta have their own probability prior distributions that might come from prior knowledge of some kind, or might be regularizers. The same with standard deviation. However, in linear models, most often, not always, but most often, we assume that all the measurements have the same amount of uncertainty. So the standard deviation is common. Okay, this is all I had prepared for today. Next time we'll have our lecture. Probably it will be during a May weekend remotely because we have some backlog of lectures. So I'll try to, because I'm not leaving, I will just give a lecture online on YouTube. No attendance is necessary, probably with better quality of transmission, and we will do some catching up on linear models and waiting time models and more advanced models of predictors in order to explain how those likelihoods actually work. Thank you very much for participation to all 9 of you, and see you next time.